Alright, welcome to week 3 everybody. This is Miss Dunn. Hope you're all doing well. I miss you all. As I mentioned in the post on Google Classroom, I'm going to be doing the lectures based on the slides that are in the weekly outline now. So hopefully that's one less thing to look at while you still get a chance to hear the lectures. So for the first slide, do now take a moment to pause, recall what is an ideal gas. Alright, so we talked about ideal gases a little while ago, back when we first introduced kinetic molecular theory, KMT. An ideal gas, so here we kind of talked about this before, but our model of gases kind of assumes they're all the same. There are these particles in like a box that are moving around. They're moving in straight lines, in random directions, and some of them are faster, some of them are slower. Their average speed kind of gives you a measure of their average kinetic energy, which is measured by temperature. When they hit the walls of boxes, that's pressure, and the amount of space they take up, that's volume. We've been looking at these 3 quantities for gases, but again, we have some assumptions about them. So what are these assumptions? One, we're going to pretend that gases are mostly empty space. The difference in size between a helium atom and an argon atom aren't that different. Kinetic molecular theory assumes that they're all really small. They're basically empty space. Second, collisions are elastic. This word here comes from physics. It means that no energy lost when they hit each other, when particles collide. And that's useful to know because if you were losing energy from the system, maybe they would slow down or something when they hit each other. Nope, they just bounce off of each other perfectly. So we don't have to take that into account. As you've seen in some simulations now, gas particles are always moving. They're moving randomly, they move in straight lines, they bounce off walls. And the particles aren't attracted to each other. These are kind of assumptions of KMT. Again, kinetic molecular theory is KMT. And there's no attraction between them. You might expect that, for instance, London dispersion forces, IMFs, they still exist in real life. Like a bigger atom might attract another one, which might throw off some of this random moving dynamics. But we're going to assume that doesn't happen. There is a poll this week that kind of looks into some of the deviations from ideal gas laws and ideal gas models, but that's kind of a focus of AP Chem. For now, we're assuming that all our gases are ideal. Again, this is not really an assumption. Number 5, it's kind of a definition. We'll remember that temperature is a measure of the average kinetic energy of the particles. And last week, the focus was that these ideal gases all obeyed certain laws. So we had Boyle's law, we had Charles's law, and we had Gay-Lussac's law. And Boyle said that pressure and volume were related in a certain way. So again, if you stepped on a water bottle that was closed, you increased the pressure, then the volume would decrease. They were inversely related. Charles's law, that's the one we looked at first, had a relationship between volume and temperature. And this is directly proportional. If one goes up, the other also goes up. So if I increase the temperature or something, heat it up, it'll expand. That's what Charles's law said. And then finally, Gay-Lussac's law was, if you look at all these variables, the only ones that we haven't compared are pressure and temperature. And Gay-Lussac's law said that pressure and temperature are also directly related. So if I increase the pressure, the temperature will go up. Or you can more reasonably think of it as if the temperature goes up, the molecules are moving around faster, they kind of hit the walls more often, then the pressure goes up. Because remember, pressure is caused by molecules hitting the walls of boxes. But in real life, all of these can only apply when the other thing is constant. So Boyle's law only works if temperature is constant. Or Charles only works when pressure is constant. Or Gay-Lussac's works when volume is constant. In real life, that doesn't happen so much. So you can kind of combine all of these into what we call the combined gas law, and see how like the P and V are on top everywhere. It turns out that P1 times V1 over T1 is going to always be equal to P2 times V2 over T2. So this kind of proportion will always hold constant. They are always related to each other in these ways. And you can see that if I hold V constant, if V1 equals V2, then that term can cancel out from both sides and you get Gay-Lussac's law. So just from this one combined gas law, you can kind of derive all the others. Combined gas law. Alright, so that was kind of a review from previous week. That's all that is. By now, hopefully, you've had a chance to look at the gas variables POGL and the gas law calculations. This week, we have two focuses. One is getting Avogadro's law. And you know Avogadro from Avogadro's number, the mole. And you can think about this question right now. The number of gas particles and volume. What would happen if you had more gas particles? Would it take up more or less volume? And the second focus of this week is the ideal gas law. These are two new gas laws, both of which aren't too bad, just kind of an extension of what we've learned already. So these first few slides will be about Avogadro's law. Okay, so at least I have this intuition, maybe you do too. For the do now, if I have more gas particles, they would take up more space. Maybe that is kind of intuitive, and maybe it's not. But if I had 1 mole of gas in like a balloon or something, 1 mole, maybe I would expect 2 moles of gas to take up twice as much space. Not like the particles themselves, but like them bouncing around or moving around at the same temperature. They might need to spread out more or something like that. Okay, so let's take a look. A lot of words in this slide. But basically, Avogadro's law, what you should know is that the volume and the amount are proportional in a certain way. So basically, it's exactly like I said. If I have 3 moles of gas at the same temperature, and let's say that takes up, I don't know, 10 liters or something, at a certain temperature and pressure, in the exact same conditions, if I had, twice as much gas, if I had 6 moles, then I would expect that to be 20 liters. That's kind of what this whole slide is saying. That's Avogadro's law. It's that the number of moles of gases at the same temperature and pressure will have, at a given temperature and pressure, an equal volume of gas will have the same number of particles, which is maybe a little bit surprising. But again, the ideal gas KMT kind of assumes that gas particles themselves are not all that different. So if I had 10 liters of gas, like of one gas, and 10 liters of another gas, they would actually have the same number of particles in the same conditions. Okay. So here's a check. Again, you can pause and think about this question, and then I'll go over it. Okay. A weather balloon is inflated with helium to a certain volume, and it goes up into the atmosphere. So if I have a balloon, it's 125,000 liters, and there's some T1 and P1 over here, and it's going to go up into the atmosphere, and I'll have some new volume, V, with new conditions, new temperature, and new pressure. And the temperature is going to go down. So this is lower. And this is also lower. So, why does the balloon rise? Turns out that this is made with helium, and helium is less dense than air. And when I say air, I mean the normal stuff that we breathe in, so oxygen and nitrogen. Helium is just less dense. We've talked about density of gases a little bit earlier last week, but helium is different, so it's less dense, it's moving up, it's rising. Less dense things are always on top of more dense things, in liquid or in gas. But will it pop? So first I might think, well, if pressure's going down, when pressure goes down, if I depressurize something, it might expand. So maybe P down means that volume goes up, and if volume got too big, then the balloon couldn't hold it, the balloon would pop. But remember, this relationship holds if T is constant. T is not constant. What is T doing? T is also going down, and when T goes down, what should happen to the volume? Well, these should go in the same direction according to some laws we learned earlier. If temperature goes down and the molecules are moving more slowly, maybe volume will go down. So then, again, this is at constant pressure, though. So kind of we see the volume goes up and the volume goes down. And you can actually see this in the combined gas law. So I'm going to write it here. So again, so P1 V1 over T1 equals P2 V2 over T2. If this number, goes down, but this number also goes down, what happens to V is that it won't necessarily go up or down. It depends on how big these two arrows are relative to each other. So we might have to do a little bit more investigation, but it won't necessarily pop at a higher altitude. Is the short answer to that. You'd have to see by exactly what percentages P and T decrease by. Don't forget that T should always be in Kelvin. It hasn't come up in this problem, but it will later on. Okay, and oops, I've already drawn on this. Let's get rid of that. Okay, so again, pause, think to yourself. Okay, so here, two closed containers, I'll draw them out. They have the same volume, so I'm going to draw them the same size, are both at 400 K. In the first container, I have helium, 1 mole helium. So maybe I'll draw that as like, I don't know, 6 particles. I can't draw a whole mole of them, but maybe just 6 of them. And then the one on the right has 2 moles of nitrogen gas, diatomic. So maybe I'll draw 12 of them. So what's the same here and what's different here? Okay, so we know that the temperature is the same. The volumes are the same, because it says that in the problem. Moles are different, also given in the problem. But what else is similar or different? So the mass should be different, because these have different molar masses, not to mention that there's simply more of the heavier one, nitrogen. Masses would be different. What about the pressure? So the pressure should actually be more in the nitrogen container. This one has greater pressure because more molecules are bouncing around at the same volume and temperature, so pressure is going to be higher for that one. All right. Think about what else might be similar or different. All right. And then this slide deck, I think this should be the final set of slides. The ideal gas law was the second learning objective for this week besides Avogadro's law. There's some recommended homework here, but what is the ideal gas law? Can we bring everything together, not just relating, one event, P1, to another, P2, but can we just calculate this for any gas at any temperature? And it turns out, well, yes, we can. So, the ideal gas law, first of all, this is the ideal gas law. You should just write it down. PV equals nRT. PV equals nRT. What do they stand for? Well, that P is pressure, given usually in atmospheres. This V is volume, usually given in liters. This N is the number of moles, number of particles, but in moles. This T is the temperature. It has to be in Kelvin. Here you don't really have a choice, unlike the other pressure and volume. You could technically give different things, but Kelvin is scaled differently from Celsius or Fahrenheit, so you have to make it Kelvin. And then this R is just a constant. It's called the ideal gas constant. And if you're measuring in liters and atmospheres, then R turns out to be this number. So we said that all these things are proportional, and this is the proportionality constant. It doesn't mean anything intrinsically. Just like 6.02 times 10 to the 23rd, that doesn't mean something. It's not like a pretty number. It's just kind of a mathematical fact that it takes this number to make everything work out. So again, you might, if you Google what R is, you might see like different values of that. If you use other units here, if you use like, I don't know, millimeters of mercury, that would change this number if you just multiply it by that conversion factor, actually, like how many millimeters of mercury are in an atmosphere, that would change this. But most often, if you stick with the standard units, you will use this R. And now, if you plug, if I tell you the pressure and the volume and the number of moles, you could calculate the temperature of any gas, because again, under KMT assumptions, all gases behave in really similar, predictable ways. All right, so here's a sample problem. You can pause and do it. I would suggest you pause and do it. I don't have my calculator on me right now, but I can go ahead and set it up at least. So N here is 1300 moles, so 1300 moles times R, I'm just going to use the 0.0821, times temperature. Temperature is 21 degrees C, but I have to convert that to Kelvin. So in Kelvin plus 273, this is Kelvin, equals, pressure is 1 atmosphere because we're at room temp, or it's probably at sea level, and then V, we have to solve for V. And in this case, there's just a 1 here, so we don't really need to divide by the 1, but you can. And then so if you do this math out, you'll actually see the volume of his balloon in liters. All right, take a moment to pause, solve this one. I'll be setting it up. So PV equals nRT. 400 is T. 1.8 is 1.8 volume equals, so 2.5 moles, 2.5. Sorry, I forgot R, but I'll put it here. And then pressure. And then I'll divide both sides by 1.8. And that would give you the pressure in atmospheres. You may have noticed in a previous slide, but it turns out that, PV equals nRT. If you plug in 1 mole, the constant is always the same, right? 0.0821. Temperature at STP, that's well defined, right? STP is defined as 0 Celsius, or 273 Kelvin, equals, well, STP, the pressure is 1 atmosphere. And you solve for V right here. If you do this math, V is actually always going to be equal to 22.4 liters. This is very interesting. It tells you that 1 mole of gas at STP is always going to be this much volume. So this is a conversion factor. 1 mole, any gas, equals 22.4 liters at STP. And as you know, conversion factors mean stoichiometry. Next week, you'll be able to do some stoichiometry problems. Actually, you already have the knowledge. You could get it started on it this week, but that'll be the focus of next week. Don't worry about it too much for now, but do write this conversion factor down or kind of know it. It's kind of helpful to have on hand. Last slide, exit ticket. So imagine you have 2 balloons, one filled with helium, and another filled with CO2. They're the same volume, in the same room, so what's similar, what's different? Again, pause, make sure you try it on your own first. Alright, so they're in the same room, so temperature is probably the same. There's no reason that temperature from here to here would be that different. So let's say that they're the same. They're in the same conditions after all. And they also have the same volume, is that right? Because it's given in the problem that the volume's the same. So if temperature and volume are both the same, because of the combined gas law, pressure should be the same. You could also think of it as they're in the same room. Like if they're both at sea level, they both have the same pressure of 1 atmosphere. That's just how it is. Balloons aren't rigid containers. They kind of equilibrate with the pressure around them. So whatever pressure we're at with the balloons, right here, then the balloons are experiencing that same pressure. Number of moles, would that be the same or different? Well, we just learned that the number of moles is proportional to the volume, and they're under the same conditions, so yeah, they should have the same number of moles. I don't really know how much, but imagine this was 22.4 liters and this was 22.4 liters. They'd both have 1 mole, just on the previous slides. But if they were both, 10 liters, there'd be a proportional number of moles as well. Okay, so all these things are the same. Is number density the same? N divided by V? Well, if N is the same and V is the same, N divided by V should also be the same. Alright, and then density of mass should have the same answer for similar reasons. If the masses are the same, density would be the same. If masses are different, density would be different. So they have the same number of moles. Does that mean they have the same mass? These are different. These should be different because helium and carbon dioxide have different molar masses. Helium is around 4 grams per mole, and carbon dioxide, I believe, 44 grams per mole. If you converted the number of moles to grams, you would see they're different, which means they must have different densities as well. Helium is going to be less dense, helium is going to float, carbon dioxide is going to be more dense than air, and it's actually going to fall to the ground. That's why if you blow up a balloon with the breath that you exhale, it's just going to fall to the floor. It won't float. Alright, hopefully that was helpful. I encourage you all to keep doing practice problems, keep doing your best. Let me know if you have any questions. And that's all for this week. Thank you.